To our webinar about the command line interface. My name is Adrian Stefan Mares. I'm head of engineering at the Things Industries, and today I'm going to be going through some advanced use cases of our CLI tool. The Things stack is an open source and also enterprise LoRaWAN stack, which can be used to basically to facilitate communication between LoRaWAN end devices and enterprise data platforms, or simply applications, integrations, depending on the use case that's required. It is facilitated by a console, which hopefully most of the users that are attending this are familiar with, a web interface. But certain, let's say, certain operations, certain advanced operations can benefit from a bit of a lower level approach using the command line interface. The command line interface, it's simply a command that we make available called ttnlu CLI or ttilu CLI, which is used to basically interact with the stack. Now, the Things stack has a unified API. So whether you are interacting with the stack via the console or you are interacting with the CLI or directly via the API, you are going to have the same experience, but certain features are made available first in the CLI, in the API, in the CLI afterwards, and finally in the console. I'm going to be showing most of my terminal workflow here. Because of this, there's going to be a lot of text, specifically text that can be copy and pasted. I've built a small file which contains all of the commands and example use cases that I'm going to be presenting today, along with some reference materials. The link will be shared in the chat. I'm going to start by sharing my screen. One moment. Yes. Okay, so great. Now my screen is available. Basically, how the flow is going to be is that I'm going to sometimes show you the console and show you different parts of the console that we use in order to interact with the stack. I'll sometimes refer to this file, which has been linked, and also via, I'll refer to it via the window that's above. So for the purpose of this webinar, I'm going to skip over installing the CLI and logging in. Those are steps which are already available on our documentation. In the link side of in the links part of the file that has just been shared, you will get information about how to install the CLI under macOS, under Linux, and also information about individual commands can also be found in the documentation. Now, my screen is a bit cluttered because I'm sharing it between the terminal and the browser, but in general, all of the links and information that I'm going to show in this webinar are going to be available via the links. There was first a question in the chat. Is it possible to initiate resending of stored archive packets via CLI in case the platform was down and data was lost, which was sent from TTI? Well, you don't need the CLI for that, but you can basically access the data. So if you had the storage integration enabled, you can query it both programmatically via the API, and then you get the messages and then you re-import them into your platform. Or later on, you can also do it via the CLI. I'll show it in a bit. Let's go back a bit to the points of the webinar. So I'm going to show up a very simple setup. So I installed the CLI, I logged in, I'm gonna choose which cluster I wanna use. In this case, I'm gonna be using a private instance of the Things stack, but you can also use the Things stack Community Edition or your own private Things stack. The Things stack has this property in which the configuration for the cluster with which you are interacting with can be saved. And this allows you to neatly separate your different CLI instances. So I'm going to make this a bit bigger. So I created the folder that is going to be specifically for my deployment. I'm going to join it, and then I can use the use command of the CLI, sorry, in order to choose with which instance I am interacting with. I'm going to be using my current one, and now I'm ready to go. I can actually run commands. And since we already had the question from the chat regarding how to get historical messages, I'll show you how you could do this. So the command which is used, it's called storage, application storage, DTILW CLI app storage or application storage. And it allows you to get you can use it to get messages. So let's say I'm interested in receiving the last, let's say the last 5 messages from the last 10 minutes. I'm going to use this, and there wasn't any message in the last 10 minutes in the application that I'm using, but yeah, sorry. So I can use, for example, this command. So app storage get, I then have to give it the application in which the storage integration is running. I can give it either a period or a limit. Check the help section of the command, and you can receive all of the payloads. Now that we went over that question, let's go back a bit the contents which I wanted to show you. Oh, sorry. So first of all, what I wanted to show is that if you want to subscribe to live traffic from an application, you don't necessarily have to do it via webhooks or via MQTT. This is also available via the CLI, and it can be quite useful in order to do some quick filtering and quick checking. So I'm going to choose the application which I'm going to use. I'm going to do this via a variable, a bash variable, which I'm going to initialize in my terminal. Let me make this a bit bigger. And then I can subscribe to all of the traffic which is sent to my application. Now, this is a bit of a fire hose. Fundamentally, there is going to be a lot of traffic which is sent to me, lots of LoRaWAN messages traffic that is sent, and I have access to all of it. Now, this is not very practical. There is a lot of information, but I don't need all of it generally when I look at traffic stream. And this is something that I could have gotten via MQTT as well, so why bother? The answer is that you can also filter this information a bit on the CLI side. And in order to do this, we will use a tool that's called JQ. It's also available in the links section of the document. And JQ has the ability to manipulate JSON documents. So for example, the command which I had before just subscribed to all of the messages, no matter what type of messages, so downlinks, uplinks, all of that. And it was, I can actually drill this down a bit and select which messages I'm interested into. So JQ works on a query basis, and if I want to build, a small query to filter the messages on, I can use this select filter that's how they call them, and just say that I'm interested only in messages which have an uplink message inside of them. Now, what's going to happen if I didn't misspell anything is that I'll see only uplink messages. Now, this is a bit better. It's only uplinks, but it's still a lot of information. Like I still have to scroll. It's a lot of JSON. You don't need all of this, and you're not interested in all of this. So let's say that you're interested in keeping only the messages which actually have a decoded payload. So basically the messages in which we turn the binary that was sent via LoRaWAN into actually something that's more human and machine readable, the decoded payload. We can do that. We simply have to increase a bit the filter. We just say that a decoded payload has to be not null. And now we're getting the messages which also have only a decoded payload. Now, there is still quite a lot of clutter in here. I still have to scroll. I don't really like scrolling. So let's do something else. Let's say that from the messages that we had before, we just want to see what end device we're interacting with, so the identifiers, and only the decoded payload. We don't care about anything else. So we're going to take a look at the last query that we wrote, and we're going to say, okay, every message that has passed this filter, that it has a decoded payload, keep only 2 fields out of them. And let's do that. I'm going to build the, first of all, I'm going to build the fields one by one, first end device IDs, and I'm asking it to keep only the top level end device IDs and the decoded payload. And I'm going to use the same path that I used during the filtering. And if I didn't misspell anything, I now have smaller messages. I only keep the identifiers and only the decoded payload. And in case I'm looking for a specific end device or a specific pattern or anything else in my decoded payloads, I can continue filtering this and basically see everything that's happening. This is a bit more convenient, in my opinion, than, let's say, subscribing to MQTT and doing the filtering in another language. In case you don't want to fire up a new script and write it and everything, you can do all of this just by subscribing to the traffic and filtering it using JQ. We can also do we can also take a look at other types of messages. So let's say we're interested, right now we looked at uplinks, messages coming from the end devices. Let's say we're interested in messages that we're sending to the end devices. So downlinks, that's something we can do as well. We go back to the first filter, which was saying, hey, keep only uplink messages. And we are going to change it to give us only the messages which we are sending towards the end device, the downlinks. We do that, and in LoRaWAN, in general, there is an imbalance. You send less messages to the end device than you receive from it. So I'm going to manually push a message to the end device just to show an example of how it would look like. Let's do that. I'm going to go to a generic node that I have in this app, and I'm going to push a message to it, and I can already see the message which was sent. And also there is also other traffic going into my app that also passes this filter. A question that comes from the chat is, can we filter by part of serial device ID? You can do both parts. So let's say full device ID. So let's show how that would be built. We go back to the original query. So we're interested in looking at a very specific device ID. Okay, so we need to look at end device IDs. Then we need to look at the device ID. And we need to check that it's equal to something. So I'm going to open the quotas. Let's copy a device ID from here. So let's look specifically at this generic node. I'm going to copy it at some point. Yeah. And if I did everything right and I didn't misspell anything, once this end device sends a message, we should also see it in the filter that we just opened here. Otherwise, yeah, and we got it. And now we filtered by a very specific device ID. But let's say you are interested in something that would match a regex. So that's also possible, like something that starts with EUI and something. For that, in JQ, you have the match, test function, and we need to give it a regex. So let's say we want everything that starts with EUI, and then we say EUI and anything else. And if I didn't do anything wrong, for every end device that starts with EUI, I'm going to see the traffic here. So the query that I used was to test the device ID against this regex that I have over here. Now back a bit to where we were heading with the traffic subscriptions. Finally, I can also look a bit at the traffic which is sent over the air. So downlink queued here is traffic that has to be sent to the end device. So an application, an integration decides, hey, we need to send a message. You're going to be getting queued. And once it's actually transmitted over the air, you're going to be seeing it in sent. So I'm going to subscribe to the traffic and look for sent downlinks. As before, we actually need to send something since we need to act like I'm going to choose one of my generic nodes and send some traffic. Or I didn't even have to, some other devices had traffic sent to it. And this is the message that I get once the message has been transmitted by a gateway. Not all gateways support this. So the gateways which use the UDP protocol support this feature in which you know that has been transmitted. Basic station gateways as well. MQTT-based gateways do not, but those are rare. So in general, you will always have this form of feedback that a message has been transmitted by a gateway. Now, one question you might get is, okay, you have those filters that you have very easily available to you that you can copy paste. That's very nice of you. How do I know what the structure of the message is going to be? And that's a fair comment. There is that as part of the documentation, there is also this message reference that I left over here. And in the message reference, you can check all of the possible message types that are going to be available via your subscription. So you can see you have uplink message, uplink normalized, join accept, downlink hack, and all of the other fields which are available can be found in the message reference in our documentation. In general, this is the most I can think of, or at least I've been able to find out for the purpose of this tutorial to show with subscriptions and with JQ. You can imagine that there is a lot more that you can do if you have like a very specific query that you're interested in building. And that's something that you can do by basically tinkering more with JQ. So piping the output that you get from our CLI into JQ, and then doing transformations or filtering or anything you need. Are there any other questions so far or use cases that you would be interested in? Let's see how we would implement that. You may write in the chat and I'll read it. And if we don't have an answer in a minute or two, we'll move forward. Okay, I don't think there are any other queries, and in case they show up, I'll just handle them at the end. Let's go a bit into the next available subject for the CLI. Let's say a CLI advanced feature that is available, and that's related to finding correlated events. So if you've used the thing stack in the past and you've looked at the message, realize that we have these correlation IDs that we carry around, these strings which are passed around quite a lot. There are many of them, lots of text, and you may be wondering what they do. The correlation ID was to basically correlate events. So as the messages are processed by the thing stack, and as they move between components, maybe to the end devices, maybe from the gateways and things like that, as they move throughout stack components, we add correlation IDs in order to allow, let's say, actions to be correlated one with another. So let's say I look at the traffic which has been of this particular uplink message of the end device that's on my screen right now. If I look at it, I'm going to see a couple of correlation IDs. So there is something here called GSCon, then there is uplink host, uplink, network servers, uplink, and some RPCs. Now, this may not tell you that much. Individual correlation IDs do have a structure, but for the purpose of what we're going to we'll be looking at today is how can I actually find correlated events? And we won't look at it from the perspective of the application, but we are going to be look at it from the perspective of the gateway. So when you look at it from the view of a particular gateway, a LoRaWAN gateway doesn't know which end device is speaking. Let's say it doesn't have the identity. It doesn't see necessarily where the what the traffic contains. So it has received a message from the air, but it cannot see what's inside the message. And let's say that you have a gateway which you have registered in your own instance, and you would like to see, let's say, what end device actually used that sent that particular message. Now, this is possible. So if you recall here from the perspective of the event, there are going to be correlation IDs. And some correlation IDs come from the gateway level. So before the traffic has been, let's say, processed. So we should be able to do a reverse lookup, starting from gateway traffic to look for application level traffic. So let's say I click on a random message that is available over here. And I have two correlation IDs. One is for the connection. This is a correlation ID that uniquely identifies a gateway connection. And second, we have a correlation ID for an uplink. This identifies an individual message that came from that particular gateway. So let's do that. Let's copy this correlation ID and let's save it in the console, in the terminal, sorry. And based on what we know about this message, we don't really know that much. We just know it's a LoRaWAN message sent on spreading factor 7, which has this frame counter and some data in it, which is encrypted, so not much. Let's see how, if there are any correlated events. So events which also occurred after the message has been processed, after being received from the gateway, and we have a catch. So let me scroll up just so that you see it from the start. We start initially, let's say, the start of the processing from the gateway server, so where the gateways connect, and we have an event which occurred saying, okay, we received a message from this gateway. It's exactly the message that we were looking at in the console, so nothing new so far. It was then forwarded first to packet forwarder, a packet broker, and then it has been received by the network server. The network server in the thing stack is this component which basically takes traffic which has been received from over the air and processes it. Processing here means finding the device which has sent it and doing the network level decryption, maybe sending some commands to the end device to control transmission parameters. But the important part here is that starting from the gateway, we managed to find which application and device has sent this message. Now that we know the message, we can actually keep going forward and we look at what happened. So the network server has received the message. Right now it came from this Dragino gateway that I had opened over the screen over here. And after it has been processed by the Dragino gateway, is the same payload, so let's say same message contents, but the next event actually shows me all of the gateways which have received this message. So I can already see, okay, this device is covered by multiple gateways, and here are all the gateways that received this message, which was sent over the air. I can also continue, and here I see that the gateway server has finished forwarding the message. Then it reaches the AS application server, and I can start already looking at the payloads. So application server receives the message, and then it forwards it. Forward in this case means go to integrations. And after it reaches forwarding, it's already decoded and decrypted. So here I have the decrypted payload. It's also decoded, so turn from binary into, let's say, individual fields, in the case battery voltage and firmware version, all of the metadata that we saw before, and also lots of extra information. Okay, then we continue. We also see that it has been stored in the storage integration, this particular message, and finally that the network server finished forwarding. And this should be all, yeah. So this was all of the information, everything that is available only from a single correlation ID starting from the gateway side. So this allows you to basically trace back, okay, I have this message in a gateway, which end device actually sent it. And it's quite powerful. But as you can see, it's extremely noisy. So we're going to be, in a minute, we're going to go over how to actually, let's say, clean up a bit the output of this command, because you can see that you have a lot of information. But before that, there is a comment. Is recalling correlation events from past packets also available in the open source version? The answer is yes. It's not enabled by default. You will have to look into how to enable event storage. So check your config file and look for event storage. After you have enabled that, you will be able to, let's say, recall historical events, first of all, and also do the correlation functionality, which I'm showing here. The duration is by default, if I'm not mistaken, 24 hours for, let's say, event metadata. So we have a separation between event metadata, so let's say identifiers and the general information of something happened, and also the actual payloads. So all of this huge data related to what was inside the packet and everything, that one is kept only for 15 minutes. So in short, 12 hours, you see, let's say that something happened, and for 15 minutes, you also have all of the data available as well. And those are configurable if you run the stack yourself. Now, back a bit to my example. So let's find a new message first of all, because as I said, the clock, the data is kept only for 15 minutes. So let's not push our luck too much. I'm going to get a new correlation ID, and I'm going to save it in my terminal. And let's say that I want to look only at the application layer information. So I'm going to do exactly the same trick I did before with JQ, and I'm going to keep only a very specific event that I'm interested in. The event is called AS Up Data Forward. It's the one which I said that is generated once the data is sent to the integrations. So we're going to do exactly the same trick. We're going to look at the event name, and we are going to filter by that, and we should have a single catch, this particular event, and we're going to have all of the information available in it. We can, let's say, do the example that was given before. So give me all of the application layer. So everything after decoding, decrypting, and everything. Show me all of that. We can do the same trick that we used before with test, which allows us to basically find by regex. So we want to test the name of the event. And in this case, we're looking for everything that's at application layer. So AS and something. So AS and dot star. And after I did that, I actually can see all of the application layer here starts. All of the application layer events. So receiving the message by the application server, forwarding it, all processed as we looked before, storing it in the storage integration, and that's pretty much it for what we have here. That would be it. It's a quite strong functionality. It also, here I've used it for the use case of going from the, let's say, gateway to the application. So finding from a packet sent over there which application it belongs to. But it can also work, obviously, with other correlation IDs. So for example, let's look for something that had a downlink. So I'm interested in seeing what caused this downlink, or what, as a result of doing this downlink, what happened. So let's save the correlation ID, and let's run the simple command. So the first one, I'll just copy paste it, no filtering, no nothing, just show me everything you have. We have a lot, first of all, too much scrolling, but you now know how to filter, so you won't have to scroll as much as I did. Oh, okay, this is too much scrolling. Finally. So this is the downlink which we have been looking at. So the downlink that we saw in the console. What happened after it was here? It was forwarded, so sent to the network server. The network server then decided, hey, I have to send this to a gateway for transmission. So the gateway basically needs to receive it. This is called a schedule attempt. We try to schedule it to a gateway. It's gonna be, if it ends up in RX1, it's gonna be sent at SF7, spreading factor 7. Otherwise, if we can fit it, it's gonna go in spreading factor 10. Okay. The gateway server, so the component that the gateways connect to, also receives it and tries to schedule. It works, so it is sent to the gateway. This is why we have this down send event. Lots of moving parts here. The network server says, okay, it has been successfully being scheduled. We sent it to the gateway. And after a while, the gateway says, hey, I transmitted the message, and we propagate this back. So gateway says we sent it, gateway server confirms it. And finally, this is propagated all the way back to the network server. So network server says, hey, this transmission has been successful. The gateway put the message over the air. And after way too much scrolling, that was it. So as you can see, lots of data that you can look into just from a single correlation ID and of tracking. You can check quite a lot of things just by looking at correlation IDs. That was what I had for correlation IDs and, let's say, tricks and what you can do with this find correlated command, which is, I would say, quite handy. As before, if there are any questions, please put them in the chat. I'm going to wait for a minute. And depending on that, we will keep moving forward otherwise. So a question from the chat, is the functionality only available for the CLI? Will the console also offer such debugging features? That's something that we've been discussing for quite a while. My colleague that works on the front end is right now hiding. But in general, the answer is yes. We do plan at one point to make this, let's say, jumping between events available in the console. At least something that we've been thinking for quite a while is having a button that says go to application from the gateway view. That would already be quite useful. But as you can see, it's a lot of data to show. Like you select a correlation ID and you get a lot of data, a lot of text that if we just show it to you, like dump it in front of you, it's not going to help that much. You would probably still benefit from this type of filtering or choosing where you want to go yourself. It's very low level, but I would say that if you need it today, use the CLI, because no matter how much we try to put it in the console, we either ask too much information of you, so we ask you to click too many buttons, or the CLI is always going to be a bit more malleable in that regard. But we are interested in basically having this find correlated available, yes. Cool. So unless there are any other questions, I think we can move forward. As before, in case you have more, just ask them and we'll answer at the end if they go to past subjects. Let's look a bit at some other information related to gateways, which is, let's say, CLI only, but for now. So if I look at an individual gateway, I can see in the console, I can already see how many messages have been received since it has connected, how many messages we sent down to it, so downlinks that went through this gateway, when was the last activity happening, and things like this. But we have more information available on the backend side relating to this, let's say, gateway connection stats. And this is available via the CLI. It's a command called get connection stats. And it allows you to see a bit more information regarding the gateway connection. So what I'm going to do is I'm going to select one of the gateways for which I want to see the information. In this case, it's a Dragino gateway. Let's also open it in the console. Is it this one? Yeah, I believe so. And now we see the uplink counter, downlink counter, when was the last downlink sent. But let's see what other information we have available. So we'll use this command, gateway LW CLI gateway get connection stats, and then we give it a singular gateway. And we are hit again with JSON. It's always JSON with a bit of information regarding how this connection goes. So first of all, we have the connected at. This is the timestamp at which the gateway has connected. In general, I would say this is not as useful as it sounds. So internet is a cruel mistress. It goes down and up quite often. We see this the most since we have quite a lot of gateways connected to us. So the fact that the gateway has been connected for a while, it's a good thing. Let's say it talks a bit about the stability of the connection, but the fact that it has reconnected recently does not necessarily mean that the connection is bad. The reconnections can happen all of the time. The internet goes up and down, as I said. So expect when it comes to these distributed systems with multiple components for connectivity to sometimes be dodgy. Then we have the protocol. Protocol in this case, it's WebSocket, which is our internal name for basic station. Basically, basic station is a protocol that's based on the WebSocket standard, so we call it WebSockets here. We can see when the last status message has been received from the end device. Status message is more relevant, let's say, more for UDP gateways. We'll get to that in a minute. But it contains, let's say, some fast information, some identifying information from the gateway. We can also look at the last status message, which has been received from the gateway. So we can see at the timestamp at which it has been received. In the case of basic station gateways, it tells us which version of basic station was there. So this is basic station 206 for the MIPS architecture on the OpenWRT firmware that Dragino uses. We also have features. So for example, the basic station build on Draginos allows RMTSH, sorry, which is a very short-handed way of saying remote shell. This is a feature that exists in basic station. And yeah, the model, which is parsed from the string over here. We then have the last uplink received at, so the timestamp at which we have received the last message, the number of messages since the connection started, when we sent the last downlink via this gateway, and how many downlinks have been sent. Then we have round trip times. Round trip times are an interesting, let's say, statistic regarding a gateway. So basically, the connection between the gateway and the network server needs to be, it has to have a certain speed. You cannot have delays of, let's say, more than a couple of seconds. And even a couple of seconds is a bit too much, because in LoRaWAN, every message that you want to send to an end device, a class A end device to be more specific, has to follow a message sent by the device. We always have to send after the device has sent a message when we speak about class A devices. So this means that if your connection between, let's say, the server and the gateway has too much latency, then you basically cannot send the messages in time. And we monitor this this particular functionality via these round trip times. Round trip type is a duration between basically going back and forth around one round trip between the networks, between the stack and an individual gateway. In the case of my gateway shown here, the smallest round trip time observed is 30 milliseconds, if I'm reading this right, and the biggest one 40 milliseconds. So it's quite good. And median, so cutting in the middle of the last 20 round trips that we did, it's about 32 milliseconds. I would say this is already way too lab settings. So I have good internet connected to this gateway, but you would be able to operate LoRaWAN with higher round trip times as well, in the order of, let's say, a couple of hundreds of milliseconds, as long as you don't do custom settings. Next thing that we can look at, it's subband utilization. This is relevant mainly for regions in which we have duty cycle limitations, like Europe, and this this basically allows us to check how much of the duty cycle has been used while sending messages. I'll show a U gateway in a bit, and we'll see what that means. And finally, the gateway remote address, which is the public IP of the gateway. This allows you to basically see from where the gateway is connected. I see a question in the chat, both via LinkedIn and YouTube. What's the best way to match between device address and gateway ID that is received for the events with device ID address on TTI? Well, it depends. So if you want to just go back, you can use the correlation functionality that I've shown before in order to go back from an uplink that what you see in a gateway to a device. You can use the filters which I've shown in the past. Otherwise, the idea is that device addresses do not uniquely identify end devices. This is something to keep in mind. So a LoRaWAN device address, first of all, it's a 32-bit identifier, so that's already not that big. It's 4 bytes of data, and generally you also lose a couple of bytes to the net ID, to the network which serves the end device. So, for example, if you saw my example from the gateway, you see that if you look at the device address, it starts with 26 and 27 in in hex. This is not a coincidence. This is the TTN net ID. So you already lose a bit, and you're left with 3 bytes to identify the end devices. Now that's not enough. We have more end devices than we actually have space here. So it can be the case, and it usually is the case, that a device address can refer to multiple end devices. So there is not a one-to-one mapping between a device address and a device ID. A device address does not uniquely identify an end device. Only the UIs or the device ID do. So you cannot go with ease, go back and forth between them. I hope that answers your question as much as possible. But since I already have this gateway open, let's take a look a bit at what else you can do with the gateway connection stats. So I looked here at an individual gateway. If you have multiple gateways, this is not going to be very convenient. So what we can also do is to look at multiple gateways at the time. I also have an Indian gateway, available over here. And I'm going to use that. So let me just let me set up the identifier in my CLI, and then I'm going to use the command, but give it exactly the same command, but give it 2 identifiers. So sorry for that. Basically, after providing 2 identifiers, I can look at multiple gateways at the same time in a singular tenant. So I have here the Dragino gateway, which I've shown before. And now I also have this new gateway, this TTEG, which is in the Indian region. And I have the data for it too. And let's say if I have a small set of gateways that I want to query all at once, I can do this by putting more identifiers into the command. Now I've been promising that I'll show how this looks for a European gateway. So first let's look for that. Which one is European in my list? Yeah, let's do this. Okay, so let's copy this device identifier, this gateway ID. Okay, gateway ID. And let's do exactly what we did before. So this is, first of all, this is a UDP gateway. So the message is gonna look a bit different. So we have the usual suspects, the connection timestamp. Now the protocol is set to UDP. And the last status message has a bit more information. So first of all, the status messages in the UDP protocol also contain sometimes the location. So if your gateway came with a GPS module, you are also going to have the location of the gateway available in the status messages. And there are also a couple of metrics. These metrics are non-standardized. In general, I can share offline a description of those, but they are not that useful. Finally, the same timestamps as before, and the gateway remote address. Now, the thing is that this particular gateway, which I'm showing right now, what happened here is that it hasn't actually any down since it has been connected. And because we didn't send any downlink, we have no round trip to verify. But that's not a huge problem because I also have another gateway available, which is basic station based. And this one hopefully should have some round trip times and channel utilizations. Yeah. So as before, we now we can check how much we have how much the duty cycle is used on a per let's say subband basis. So in the EU, there depending on the transmission frequency, we have different duty cycle limitations. So for example, in the frequencies between these two, so in this range, I'm not gonna read it out loud. We have, let's say, 1% duty cycle limitations. For the next subband, we have 10%, and there are also bands with 100. Sorry, this is 10%, and this was 1%. My bad. The idea is that for every subband, we are going to have the limit depending on what has been used. And also we are going to have the utilization. This particular gateway, even though it has sent some messages, you can see that it's weird. So we have messages sent, but there is no utilization. What does this mean? What actually happened here is that the last message was sent yesterday. If we check when the last message was sent, we see that it was sent on the 15th. And duty cycle is calculated over the past hour. So obviously, since we sent the message over 24 hours ago, we don't really have any utilization left, which is why the fields are missing here. But that's not a problem because of this gateway, I have yet another gateway. I have too many of those actually. So I have femtocell gateway, and let's see if it has sent something recently. Otherwise, you'll just have to believe me that it works. Yeah, finally. Yeah, so this one has sent messages. First of all, let's look at the timestamp. So this one has sent messages quite recently, almost 1 hour ago. And because of this, we have some utilization. So we can check that this part, some parts of the subbands have been used. Now, what happens if the utilization matches the limit is that we can no longer send downlinks through that set of frequencies, through that range of frequencies, until the duty cycle, so the utilization goes down below the limit. So in case you are looking, let's say, at the gateway and you see some messages that say, hey, I cannot schedule a message via this gate, general answer, if you look through the events, is going to be that the message wasn't sent through that gateway because the utilization was too high, and you would break basically radio regulations if you were to send that message. Other than that, that's it for gateway connection stats. Yet another thing that you can use while you debug gateways, some extra information, some extra behavior that you now are aware of. If there are any other questions, please ask in the chat and I'll try to answer. And in a minute, we'll continue to the last part. Okay, so since we didn't have any extra question regarding gateway connection debugging, we can move to the last section of the webinar, which is related to ADR settings. ADR comes from adaptive data rate, and it's an algorithm that occurs between the end device and the network server in order to lower the data rate that is used for transmission. So in LoRaWAN, we have multiple data rates at which we can send messages. Depending on the data rate, we can send more data, first of all. So let's say as the spreading factor goes down, we lower the range, but we also lower the power used and we increase the data which can be sent. And also the opposite is true. So we can also increase the spreading factor. We will have to send smaller messages, but we can send them over higher ranges. Now, the idea is that ADR itself is an algorithm that looks at, let's say, at radio parameters, but it has some main tuning knobs available. So something that may be of interest to you is, let's say, the number of transmissions. So in my perfect lab environment, which I've been here, all gateways are near the end devices. There is no sort of radio interruption. Everything is crystal clear, almost too crystal clear, and there are no problems. Now, this is the difference between a laboratory and the real world. The real world is not that pretty. And in the real world, there is interference. There is what is called multipath, so the same message coming through multiple, let's say, paths. So air paths goes through two possible ways. And because of this, you may actually end up losing some messages. Now, one tuning knob that is available to deal with this is the number of transmissions. The end device can be instructed by the network server to send the same message multiple times. So in case you are basically having bad transmission, in order to improve the reliability at the cost of battery, you can increase the number of transmissions. And what happens is that the end device will send the same message multiple times in the hope that at least one of the attempts will go through. This is called in ADR terminology number of transmissions, also known as MB trans. And sometimes you want to tune it. So let's say you say, I can lose some data. It's fine for me to lose data. I want to preserve battery. And in such situations, you will be interested in what your main interest is to limit the MB trans. You don't want to let the network server ask the device to send more often. Now, this is something that can be done. This can be done via ADR settings. So I'm going to be doing that in a minute. First of all, for the purpose of this experiment, I'm going to select a particular application and a particular device, a generic node, and it's going to be the node that I have here in the console. Now, let's start with the basics. I'm going to remove all of the settings that I have already related to ADR. I just want to use defaults. This is done by using the device set command, and then we have an unset parameter that basically allows us to remove any ADR settings from the end device. So I'll do just that. Now I've removed all of the settings available. I'll skip and we'll come back to it in a bit. And let's say I want to use only MB-Trans 2, or I want to use most MB-Trans 1. I'm going to set it to always use 2, so always transmit twice. And this is quite a mouthful, but I'm setting max settings, ADR mode dynamic, mean MB-Trans, so minimum MB-Trans to 2, and maximum to 2. Now, what's going to happen, or at least should happen, is that I'm going to send a command to the end device that says, hey, transmit twice. It's called the link ADR request with the number of transmissions set to 2. And I send it, the end device receives it and responds to it, acknowledges the fact that it has to now send the same message twice. And all of the messages that I'm receiving from this point forward are going to be doubled at network layer. So here is the first receival, and I also see it at the application layer, decoded, decrypted, everything beautiful. And a bit above, I can also see the second transmission. This is why you see here receive data message, process data message, but no decoding taking place, because we also make sure that we send to you at application layer only one of the transmissions, even though we process both. And this is a use case. So in this case, I'm always using 2, but you can imagine that if you set both the min and the max to 1, you can force it to send only one transmission, no matter how bad the parameters are. I can also do the same for other parameters. So for example, I can limit the data rate and which the end device operates. So let's say I want it to stay always on SF7 or always on SF8 or something like that. There are many parameters available, and you can find them a lot easily if you just grep. What I mean by grep here is that we look at the device set command, and we are going to be looking at only max settings, ADR mode, dynamic. Oops. And obviously, if I want to give me help text, I need to pass --help. And here I can see what kind of parameters are available in the dynamic ADR mode. So margin, this is described a bit in the documentation, is basically how much margin of error is available for this ADR manipulations, maximum data rate, which is allowed, maximum number of transmission, maximum transmission power index, and also the same variance for minimum. And based on this, you can build your own command and manipulate a bit the ADR algorithm. There is a question in the chat: do ADR transmission settings require a certain minimum LoRaWAN device, LoRaWAN version on the end device? The answer should be no. Fundamentally, the link ADR request command, basically the command that the network server uses to ask the end device to, let's say, use a specific data rate or a specific number of transmission, has always been available. So that's good. The meaning of these data rates changes between your region. So the catch is that LoRaWAN depends because it runs in the unlicensed spectrum. It doesn't have the same transmission parameters everywhere. So we have some in Europe, there are some in the US, there are even 2 in Australia. Asia has way too many. So and every single the meaning of, let's say, those data rates, like the minimum and max, let's say, changes depending on the region in which you operate. The LoRa Alliance has a document called LoRaWAN Regional Parameters, which basically tells you what the meaning of each one of these is. But your main takeaway from here should be that, yes, you can use it with any LoRaWAN version. And 2, it depends on where your device operates on what the parameters should be. That's the main one. As I said before, there are also other use cases. So ADR is something that is generally working very well when the device is static, so it doesn't move, and we just have to adapt the radio transmission parameters based on the things that changed in the environment, so between the end device and the network server. But that's not always the case. So popular LoRaWAN use case is tracking, and tracking, for example, uses movable end devices, and there you don't want to actually use ADR that much, or at least you only look at the transmission parameters, because you look at something historical. So you look at what happened in the past and you try to use that to determine the future. But what happened in the past while you were, let's say, in a city may not hold while you're in the countryside. So ADR is very useful when everything else considered stays the same. Whereas if you are moving, your radio parameters are continually changing over time. In such cases, you might be interested in always staying on the same radio transmission parameters. And I'll come back to the question regarding how the spreading factor is chosen in a minute. You want to stay, let's say, on the same radio parameters. And this is also possible. We call it static ADR, static as in don't change anything, depending on what's happening in nature. And I'm going to go exactly through the same steps. I'll unset all of the settings that we had in the past. And I'm going to use the static ADR command. Now, this is again a mouthful, I'm sorry. The static ADR command in general requires 3 parameters. So data rate index, in this case, this is data rate 2, in the EU, this is SF10, and the number of transmissions. And the third parameter is the transmission power index, but that's optional. 0, it's also a valid value. So after doing this, I move the end device into static ADR. Basically, static here means stay in the same within the same parameters. And upon the next message, basically, I'm going to say, hey, move to data rate index 2 and send only 1 transmission. Now we're going to wait for the device to respond to our request. It should happen, I think, in a couple of seconds, so 10 or 12. And while we wait for the response to come, the question is, how does the LNS decide which spreading factor to use for the device? The answer is mainly based on SNR, on signal to noise ratio. So this value, depending on the SNR from the best gateway on a historical basis, we check how much, how much we are allowed to ask the device to use less power without sacrificing reliability. Going back, the device has already spoken too much, but it has also confirmed our request to use spreading factor 10 and only 1 transmission. And we can also see this here. All of the subsequent messages are on SF10. That was it for ADR, basically. These are the main modes which are used. There is also a disabled mode, but that's not very interesting in general. If there are any other questions related to, let's say, those ADR modes or ADR settings or the CLI in general, I'm waiting for them in the chat. Otherwise, in a minute, we'll wrap up the webinar. In the meantime, let's check if I unset everything. It should just go back to spreading factor 7 because the signal is pristine. But when you don't test these things, you don't know what's going to happen. So let's see. Okay, so yeah, it moves to spreading factor 7 and 1 transmission. And the end device should also approve this in 30 seconds or so. And it worked. Good. If there are no other questions available, then I think we should wrap it up here. And if you have any other questions, please contact us either via the forum, via the support page. Thanks everyone for the questions. They were really nice. The commands which I've used and copy pasted around are available in a document that will be available in the webinar description. And you can copy paste everything from here too. It's only the commands. So look at the webinar, let's say recording next to it. But yeah, that was it. Thank you for having me and have a great day. Bye-bye.